Hey guys, I'm Jay. Today is my LeetCode review one take vlog on 200th problem, number of islands. We are given a m times n 2D binary grid, which represents a map of 1 and 0. 1 is land and 0 is water. We'll return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. We may assume all four edges of the grid are all surrounded by water. And let's see example 1 here. We got empty grid here and the output is 1, as all the ones are connected into one island. And let's see example 2 here. The first island is here, and the second island is here, and the final island is here. So our output is 3. Okay, let's get into our intuition of this problem. The key idea is to scan the grid, and when we meet a cell with a 1, we perform a traversal using depth first search or breadth first search to mark all connected land cells as visited. So each traversal will cover one island. Alternatively, we can use a union find data structure to solve this problem too. Then, let's get started with our first solution, depth first search. And the idea is very simple, depth first search. The idea is pretty simple. We traverse the grid cell by cell. When we meet a 1, which means an island is found, then we'll use the depth first search to sync the entire island by marking all connected lands as visited. This prevents counting the same island more than once. And let's get into the code. We start by checking if the grid is null or empty. If there is no grid at all or no rows, there is nothing to process, so we should immediately return 0. If grid returns null, or grid.length equals null, we just return 0. Next, we initialize our island counter to 0. We also determine the number of rows and columns in the grid. This helps us when we iterate through the grid and in our depth first search helper function. We declare an integer variable named num_island, started at 0. We also initialize rows as grid.length and columns as grid at 0 index at index 0 length. Then we use nested loops to iterate over every cell in the grid. The outer loop goes through each row, and the inner loop goes through each column in that row. First, we create a for loop here for integer I started at 0. When I is less than rows, we continue the loop, and after each iteration, we increment the I. And for the inner for loop here, integer j started at 0 when j is less than columns. We continue the loop, and after each inner iteration, we increment j. And inside the loop, we check if the current cell is 1. If it is, that means we found an unvisited piece of land. If grid at row of I and column j is equal to character 1, which means we found an unvisited piece of land. So we'll increment our island counter. Num islands plus plus Meanwhile, we also call the depth first search helper function to mark all connected land cells as visited to ensure that we won't count them again later. Depth first search, we call depth first search method with greet I and j. And after processing every cell, we return the final count of islands. Each depth first search call ensures that one island is completely processed, so our counter is the total number of islands. We'll return islands, num islands. Now, let's implement the depth first search helper function. We'll declare a private method named depth first search, which would return void. And this method needs three variables. First is an array named greet, and the second is the index I, and index j. We start by getting the number of rows and columns in the greet. We initialize rows i's greet.length, greet.length, and columns as greet at index 0.length. Then we check if the current cell is out of bounds or is already water. And the condition is if I is less than 0 or I is bigger than or equal to rows, or j is less than 0 or j is bigger than or equal to columns, or if the current cell is out of bounds or if it is already water. And the condition is greet of row I and column j is equal to character 0. If either condition is true, we simply return because there's nothing to process. Or, if the current cell is valid land, we'll mark it as water to ensure the subsequent iterations don't count the same island again. Greet of row I and column j is assigned to character 0. Finally, we'll recursively call the depth first search for the 4 adjacent directions up, down, left, and right. These calls will continue to mark all connected pieces of land. First, we call the depth first search with the upper up direction. And the first parameter is the greet and I subtract 1 and j. Then followed with depth first search with greet I plus 1 and j. And the third one we call depth first search with greet I and j subtract 1, which is the left direction. And the final one, depth first search with greet I and j plus 1. Once all recursive calls complete, this depth first search function will return control to the main function, where we'll continue scanning for the next unvisited piece of land. Alright, that's all of the code. Let's submit our code and check if our solution passes all the test cases. Yes, our code got accepted. Now, let's dive into the time and space complexity analysis. So the time complexity, it is big O of n times n, where m is the number of rows and n is the number of columns, because each cell is visited only one time. And for space complexity, it is also big O of m times n. In worst case scenario, when the grid is entirely length, so the recursive depth first search could go as deep as big O of n times n in the call stack. But for most typical cases, the depth will be much less. And this is the first approach. Then let's get into the second approach, breadth first search. Breadth first search. First search. Now, I will share a breadth first search solution. This approach is similar to the depth first search. We start from each one and mark the entire island, but we use a queue to explore the grid level by level. We add a starting cell to a queue, and when the queue is now empty, we pull a cell and check its neighbors. Each neighbor that is 1 is marked as visited and added to the queue. This loop will continue until the entire island is processed. Now, let's get into our code. First, we'll check if the grid is null or empty. And it is very similar to the first approach. If grid is equal to null or grid.length equals 0, we are return 0. Next, we initialize the island count and determine the number of rows and columns in a grid to prepare for iterating over every cell in the grid. Integer non-islands. Integer non-islands starts at 0. We also initialize rows as grid.length and columns as grid at index 0 .length. We then loop over every cell in the grid. Then the nested loops ensure that we check every row and every column. So we will create a nested for loop here. Integer I started at 0. I should be less than rows, and increment I after each iteration. For integer j started at 0, j should be less than columns. Increment j after each iteration. When we found a cell that contains 1, we increment our island count and call the breadth first search helper function, which will traverse all connected land cells and mark them as visited. If grid of row I and column j equals to character 1, if so, we increase the island count, non-island. Then we start the breadth first search from this cell. Breadth first search with grid and index I and index j. After processing every cell, we'll return the final count of islands. Each breadth first search call ensures that one island is completely processed, so our counter is the total number of islands. Therefore, we just return none islands. Then, let's move on to the breadth-first search helper function. Its purpose is to traverse every connected one, starting from the given cell and mark them as 0 to avoid double counting. We declare this method as private and return void. And the name is breadth-first search with 3 variables. First is a character array called greet. Then is integer I and integer j. We also start by getting the number of rows and columns in the grid. Integer rows started at greet.length and integer columns started at greet at index 0 length. Next, we set up our direction vectors array to easily explore neighboring cells in 4 directions: up, down, left, and right. Integer array called directions is assigned to -1, 0, +1, 0, 0, -1, and 0, +1. We then initialize a queue for breadth-first search. We add the starting cell and immediately mark it as visited by changing its value to 0. Queued off integer array. Let's call it queue, and we initialize the queue as a new empty linked list. Then we add the starting cell into the queue, and the code is queue.offer with a new integer array of I and j. Then we mark this length as visited. Greet of row I, column j is assigned to character 0. After that, we process the queue until it is empty. While queue is not empty, we'll continue the while loop. And inside the loop, we retrieve and remove the H cell of the queue. Integer array of cell is assigned to queue.poll. Then we get a row and column and create an enhanced for loop to check its 4 neighbors. Integer row is assigned to cell at index 0, and integer column is assigned to cell at index 1. Then we create an enhanced for loop to check its 4 neighbors. For integer array, called D, and directions. Inside the for loop, we calculate the row and column of the neighbor cell. Integer new row is assigned to row plus D at index of 0. And new column is assigned to column plus D at index 1. Then we check its bounds and whether it is length. If new row is bigger than or equal to 0, and new row is less than or is less than rows, and new column is bigger than or equal to 0, and new column should be less than columns. And grid of new row and new column should be character 1, which means it's a length. Then we'll mark the cell as visited and add it into the queue for next iteration. Grid of new row and new column is assigned to character 0. At the same time, we'll add it into the queue. Queue.author with new integer array with the new row and new column. When the iteration completed, the breadth first search function will return control to the main function, where we'll continue scanning for the next unvisited piece of land. Okay, we have completed the entire solution. Now it's time to submit our code and see if everything works as expected. Oops, I spelled the word wrong here. If grid is equal to null, let's resubmit again. Yes, our solution passed all the test cases. Then let's break down the time and space complexity. So the time complexity, it is still big O of n times n. We iterate over every cell in the grid, which gives an big O of m times n time complexity. M is the number of rows and n is the number of columns. The breadth first search ensures that each cell is processed only once. And the space complexity, it is still big O of m times n. In the worst case, this worst case happens when the grid is entirely land. The queue of the breadth first search would hold all the cells. But for most cases, the space cost will be much less. And this is the second solution. Lastly, I'll briefly explain an alternative solution using the union found data structure. Union found data structure. Here, every land cell is treated as a node in a disjoint state. Initially, each one is its own parent. We then scan the grid and union adjacent land cells. Every union operation merges two islands, and the final count of the disjoint cells gives number of islands. This method is inefficient and elegant for handling connectivity problems. And let's get into our code. We begin with a simple edge case check. If the grid is null or has no rows, there is nothing to process. So we'll return 0. If grid is null or grid.length is 0, we'll return 0. Next, we retrieve the rows and columns of the grid. We initialize rows as grid.length and columns as grid at index of 0.length. Then we create an instance of the union found class that initializes every len cell as its own component. Union found, let's call it UF, is assigned to a new empty union found. Union found with grid. We then iterate over every cell in the grid using nested loops. For integer I starting at 0, I is less than rows increment I of each iteration. Then we implement the inner for loop. Integer j starting at 0, j is less than columns. J should be increment of each iteration. And for each iteration, when we encounter an 1, which is a len cell, we'll mark the entire cell as visited. If grid at row I and column j is equal to character 1, we'll mark it as visited. So grid of row I and column j is assigned to character 0. At the same time, we'll set up our direction vectors array to explore neighboring cells in 4 directions. Integer array with directions is assigned to -1, 0, +1, 0, 0, -1, and 0, +1, which is the 4 directions. Then we create an enhanced for loop to check its 4 neighbors. For integer array called D and directions. Inside the enhanced for loop, we calculate the row and column of the neighbor cell. Integer x is assigned to I plus D at index of 0. Oops. Integer y is assigned to j plus D at index of 1. For each neighbor that is within bounds and is land, we perform a union operation to merge the 2 pieces of land. And the condition is if x is bigger than or equal to 0 and x is less than rows and y is bigger than or equal to 0 and y is less than columns. And grid at row x and column y is equal to character 1. Then we'll merge the 2 pieces of land. UF.union with I times columns plus j and x times columns plus y. After processing all cells, the total number of disjoint cells in our union found structure is the number of islands. So we just return it. Return UF.getCount. Now, let's dive into our union found class, which is the core of our solution. We define a class named union found. Then we'll declare several variables. First is a private integer variable named count. Then is an integer array named parent. Private integer array named parent. Then we'll implement the constructor method public union found with the greet character array named greet. And inside the constructor method, first we calculate the total number of cells by multiplying the number of rows by the number of columns. Integer rows is assigned to greet length. Integer columns is set to greet at index 0 length. Then we initialize the parent array and the count variable. Parent is assigned to new integer array, and the number is rows times columns. And we initialize count to 0. Next, we create an enhanced for loop to initialize the union found structure. For integer I, starting at 0, I should be less than rows, increment I of each iteration. Then we implement the inner for loop. Integer j started at 0, j is less than columns, increment j of each iteration. Inside inner for loop, for every cell that contains a 1, we'll map its 2D position into a 1D index. If greet at row I, column j is equal to character 1, then we map its 2D position into a 1D index. Integer index is assigned to I times columns plus j. At the same time, we also set the parent of that index to itself, because each length cell is its own parent. Parent at index of index is assigned to index itself. Then we increment our island count as each one starts as its own island. We increment count. Then we'll implement the found method. The found method uses path compression to find the root of a node, so that every time we search for a root, we flatten the structure by pointing nodes directly to the root. We declare the find method as public. It would return an integer, and the name of it is find with the index. If an element is the root of its own set, then parent of I would equal I. If parent at index I is now equal to I, it means that I is not the root, so we need to look further up the chain. If parent at index I is not equal to I, we make a recursive call to find parent at index I to find the root of I's parent. Parent at index of I is assigned to find parent at index of I. As we go through this recursive process, we set parent at index I to the result of find parent at index of I. This would effectively compress the path by directly linking I to the root. So we just return parent at index of I. Then we'll implement the union method. The union method merges two components and decreases the count if they were separate. Public void merge with two parameters, integer x and integer y. First, we found the roots of both elements. If the roots are different, we link one root to the another and decrement our island count because two islands have now merged into one. Integer root x is assigned to find of x. Integer root y is assigned to find y. If roots are different, we'll merge them. If root x is not equal to root y. We link one root to another. So parent at root x at index of root x is assigned to root y. Then we decrease the count of islands because two islands have now merged into one. We decrement count. In the union found structures, every element belongs to a set or component that is represented by a root. So when we call the union operation for two elements, we first found their respective roots. If the roots are the same, it means that they already belong to the same connected component. There is no need to perform another merge since doing so won't change the structure of a set. It would simply be redundant. This is why in our union method, we only merge if the two roots are not the same. Finally, we'll implement the getCount method, which is simply easy. We just return the count variable. Public getCount. We just return count. Alright, let's submit our code and check if the solution works. Oops. Public void getCount method. Let's resubmit again. Union found. Cannot found symbol. Union found. There is a new keyword here. Cannot found symbol. Union found that union. Where's the union method? Union method is here. Let's call it union. Let's submit again. Get count. Oops. The return type is wrong. It should be integer. Let's revise it and resubmit again. Yes, our code passes all the test cases. Now, here comes the time and space complexity analysis. The time complexity, it is also big O of n times n, because we traverse every cell in the grid once. So the time complexity is big O of m times n. M is the number of rows and n is the number of columns. The union and found operations are mostly constant time on average due to we use the path compression. And for space complexity, it is also big O of n times n, as we maintain an array to represent the parent of each cell. And the recursion in the found method uses little extra space due to the path compression. And this is the end of my LeetCode review vlog on this problem. And I highly recommend you guys to visit my online GitHub page here, which contains the problem description, intuition and ideas, and different solutions with very detailed annotations, and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the codes and nodes to build this online GitHub page. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.